Now let's talk about differentials. This says let z equal fxy be a function of two variables with x0, y0 in the domain of f. And let the change in x and the change in y be chosen so that x0 plus the change in x, comma, y0 plus the change in y is also in the domain of f. If f is differentiable at a point x0, y0, then the differentials dx and dy are defined as dx equals change in x, dy equals change in y. So what it's saying here is that those differentials are going to equal the actual change in x, the dx, and the dy is going to equal the actual change in y. Not an approximation, the actual. And it says the differential of z is also called the total differential of z equals fxy at x0, y0 is defined as f of x0, fx, x0, y0 dx, and fy, x0, y0 dy. So in this instance, the total differential, the dz, is actually what would be approximated here. You guys were first introduced to differentials when they talked about linear approximation or linear approximations or tangent lines. This is the first case where you've actually dealt with differentials. So for instance, if I had the function f of x equals x squared, you would say the differential would be, because this is the same thing as y equals x squared, you would say dy equals 2x dx. And you've seen this kind of notation also when you dealt with the idea of doing a u substitution. So that's what a differential is. So now if I was dealing with f of x equals x squared and I found the differential, the dx actually equals the actual change in x. The dy is an approximation. And generally you approximate from a point when we talked about tangent lines. Now we're talking about tangent planes here. So that's why we get a differential of z here, because that's just going to be an approximation of the actual z value. And that's what happens here with dy. Now let's say I did pick this graph around 0. I'm just going to draw that really quick. I want you to see something here. Now think about this. I just drew the graph here. I put the tangent line in, and that's the purple line down here. I put in the f of x equals x squared. That's the red one. So that's this one here. And then I also put in here some points. Now when I created this tangent line here, I did it with respect to x equals 0. So that's why it becomes a horizontal line there. And what I want you to see from here is if I actually move to the right here, 1, so my change in x would be 1, and it wouldn't matter if I use the actual function, which is this, or if I use the approximated, the linear approximation at x from x equals 0. So it wouldn't matter which one I use there, the change in x would still just be 1. And that's what it means here, that doesn't change because that's my independent variable. Now what changed was that dependent variable. Now my y changed here. The dy here would actually equal 0 because there was no change in elevation. And when I think of up and down, that's my change in y. And that's what dy means. It's an approximated change in y for this one here, because y is my dependent variable. But if you look at the other point actually on the graph, the actual change in y, and it's written this way, that equals 1 because I went up 1 from 0. Not 0 from the center there, but if I look at anywhere on this line here, that's 0. My y is 0 there. So it actually went up 1. So my actual change in y is 1, while the dy is 0. Now again, that happens with these dependent variables. So now when we actually look at the function over here, this is just in general now, when I look at this, the x and y are independent variables, so that's why they have dx equals change in x and dy equals change in y. They're equal to the actual. And what's different here is my z, because we see the actual z value, and that's down here. And then here is the approximated one, and that's sitting on this plane. So hopefully that's easy to see. So that's going to be my approximated one. That's just like my tangent line here. That was the approximated one. So there's no difference here except it's three-dimensional now. And we're dealing with planes instead of lines. So that's the only difference here. So that would be the actual change in z. And then this one up here would be the, what we'd call the dz. Now remember how that's working here. So here's the z. This is the point of perspective here. Now that's the first point. Now however that changes, does it go up? Does it really go down? That's going to be the difference. This z value might be up here and this z value might be down here, depending on the plane, of course. So that could be more in an upward direction, so, or it could be closer, depending on how close to the point I am. But the closer to the point, the closer that dz and change in z are going to be. And I mean change in z. Okay, so anyways, let's take a look at the problem now. Now the problem's actually a lot easier than this, but I wanted to give some concept beforehand. The further I go out, the further probably dz and change in z would be. So anyways, let's take a look at this problem here. So this one says, find the total differential of the function w xyz equals ey cosine x plus z squared. So what we're going to do here is we're just going to do the same thing as this. Now I want to do this one because this one's a little different, because this one here is only set up for functions where z equals fxy. But what we have here is we have a w function. So that's a four-dimensional function we're looking at down there, which is different from the definition. So I'm going to show you how this extends. So this here would be my dw. And what I have here is fx, x naught, y naught. Oops, let me just draw this out so we're not wasting time. So this is what we're actually looking at here. It's just a simple extension of it, because now I have another variable, another independent variable, I should say. So now all I'm going to do is just, what is wx? So for the first one, I'll do that one. Now this is my term that has a variable x in it, and this one doesn't, so that z squared is actually just going to be 0, because the derivative of z squared with respect to x is 0. Z is a constant in that sense. It's treated that way. So this is going to actually be, and e to the y is going to be a constant too, because that's just a variable there, and it's not z, and it's not x. So therefore, it's going along for the ride. So this is going to be negative ey sine of x, and the negative because cosine of x, the derivative of that is negative sine of x, and that's why I'm writing that. And then I would say dx. So that's this piece here, and then dx. Okay, now we're going to do the next one. So plus, now wy. So now we're taking the derivative of w with respect to y now. So again, this is going to zero out because that's just a constant, because it's with respect to y, not z. And e to the derivative of e to the y is e to the y. Cosine of x is going along for the ride, simply because it's not doesn't have a y in it. So that's just cosine of x. Okay, and that would be dy. And then the last one then is going to be plus. And then now we're dealing with the z here, because it's wz. And that's going to be, this is going to be 0 then, because that's all just a constant. So I'm going to get 2z, and then I'm going to write, oops, did I forget it? I did. I forgot it for the other two. Because they're differentials, I have to put those dy's and dz's in there. So it's adjusted in the last second. I'm super fast. Okay, so for that dz, I would have 2z dz. And if you can see, I put that in for the y as well down here, but I didn't have it in the formula originally. So this is just a modification of that. And this is actually going to be my dw. So here's the answer for that. That's my total differential. So they're not too bad to do. It's just derivatives. But that's my answer there. So just make sure you fix that and make sure you write that in correctly. That was my hang up on that one. Even though I had it in the answer, I didn't have it in the formula. So I apologize for that. So there it is.